Okay, so here's what we were talking about. Here's what we were talking about last time. We were talking about directional derivatives, and let me remind you what the construction is here. So we have a function, multivariable function. It's got a domain. It's got a target. We find ourselves at a certain point in the domain, right? And therefore, there's a corresponding image. Right? But we are not just at the point A, we are at the point A and moving with some velocity. So the question that we face, and this is motivated by the classical construction of the derivative in single variable calculus. If we're moving with a certain velocity in the domain, what is the corresponding velocity in the target? Right? Now, to say this a little bit more generally, given an input change, what's the corresponding output change? Right? So be this a rate of change, or perhaps instead like a discrete jump change. Right? But again, for my own personal intuition, and I think the algebra works out a little bit more easily, I find it more convenient to deal with velocities. Okay. All right. So what we talked through last time was how we'd go about finding a relationship, given an input vector. What is the corresponding output vector? And the idea was to take that input vector, use it to actually make an actual parametric curve that is at that point A moving with that velocity. Right? Realize this as an actual function. And we get that with this formula. There's an actual parametric line that when t is equal to 0 is at the point A moving with velocity v. Well, if you have this input curve, x is a function of t, right? Then you can plug into the function f and get this corresponding output curve like that. Right? So the green curve is our sort of premise parametric curve in the domain. The blue curve is the corresponding image curve in the target. And so let's remind ourselves, our goal here was to, associate, given a given input velocity, we wanted to find the corresponding output velocity. Well, that output velocity is just the derivative of that blue curve. Okay, so put that all together. You get this formula right here. We give a name and some notation to this. This is called the directional derivative. Here's the notation we use. We talked about the notation last time, so I won't go through that again. But directional derivative. Okay, let's move on. This is what we were talking about last time. Move on and talk about some interpretations. The first two interpretations I have here are just observations of what we were computing in the first place. Our goal was to assume that we had a vector that represented input changes. Input changes. Now, it could be a velocity, right? Could be a discrete jump. Some way or another, some sort of an input change, which we always represent by a vector. So, again, reminder, I've said this several times now, but sometimes I'll just talk about an input vector. The input vector means a vector representing some appropriate form of input change. Given an input vector, the directional derivative is just what is the corresponding output vector. Velocity or jump or whatever. Okay. All right. Some special cases. Suppose that your function is real valued. Well, okay. Now keep in mind what a directional derivative is. Directional derivative says, input vector, corresponding output vector. So if your function is real valued, what that means is that it's a multivariable function, but the function represents just a scalar value, some quantity. It represents let's say temperature, right? So maybe here's the map of our local region where we live, and there's a function that tells you at any given point. At any given point where you might happen to be, there's a corresponding temperature at that point. And so the interpretation you would make of directional derivative here is if you're at this point and moving with a certain velocity through our surroundings where the temperature is not fixed, the temperature is maybe it's warmer here and maybe it's cooler as you head uphill into the mountains, cooler temperatures up there. So if you're moving with some velocity, the directional derivative just says how fast is the temperature changing that you are experiencing as you're moving through this non-constant domain. Function, this function where the domain, the function has different values at different points in the domain. Okay. So rate of change of whatever quantity you're interested in. Okay. Now, on the other hand, what if the domain is one-dimensional? Well, it turns out then it is pretty easy to relate this to a parametric curve. The entire image of the domain is a curve. We're viewing position as a function of a single variable. It's pretty natural to expect that this is a parametric curve, and the directional derivative being a derivative wouldn't be too surprising to think of that as being a lot like a derivative of a parametric curve. And in fact, it is, with one little asterisk. Keep in mind, when you talk about a derivative of a parametric curve, you're talking about velocity per unit time. Keyword unit. Right? So this v has to be the unit vector in the, that v has to be 1. It's a vector in a one-dimensional domain, so it has one coordinate, so it's really a number. So that vector's got to be 1 so that we can interpret the directional derivative then as being velocity or rate of change of position per unit time. Okay, so that's something that's easy to check, and you can write down the algebra. In other words, if you want to take that function and just write down what is the derivative of that parametric curve when v is equal to 1, write it all down. Note, it is exactly the same formula as the directional derivative. Yeah.
Also, just to clarify from the parametric curves, if you're asked for the speed, is that the magnitude of the derivative vector at that point?
That's right. So the derivative vector is the velocity vector. Right? Vectors, both vectors. So the word speed, you're quite right, is intended to refer to the magnitude of the velocity vector. Namely just the rate of change of, distance traveled per unit time. Yeah. Yep, totally. Okay, so let's do some computational examples. Here's a multivariable function. It's a function from R3. Note there's 3 input variables. Into R1, notice that there is 1 output value. And let's compute a directional derivative of this function. Now, keep in mind that if you want to compute a directional derivative, let's go back to our definition. A directional derivative of a function requires that you tell me where are you and what's the input velocity. Right, so it's not like taking a derivative of a, in single variable calculus, you say the derivative, and it's the derivative at a certain point. And the assumption is, in other words, that you're talking about, the rate of change of the function per unit change in the input. So again, the assumption is that the input change is 1 when you're doing single variable calculus. Here, we're not making that assumption. We're assuming that we have an input velocity as indicated by that vector there. Okay, all righty. So the question we're looking at here, there's our function. And we're going to assume that in consideration of that function, we are momentarily at that point and moving with that velocity. So we have an input point, we have an input velocity. We want to know what is the corresponding output velocity, namely what is the rate of change of the function. Okay, so directional derivative. Right? But by construction, the rate of change of the function is the directional derivative. So the question really is purely computational here. The idea is we just want to take the definition that we have of directional derivative and plug and chug. So let's do that. This point A is that. This velocity vector V is that. That means that the parametric curve, the input parametric curve, A plus TV, this parametric line that we have here in the domain, right, is given by this formula. There's the A, there's the V, there's A plus TV. Multiply it out, combine terms, there's the input parametric curve right there. Okay. What do you do with the input parametric curve? Well, you plug it into the function to get the output parametric curve. Alrighty, so we're going to plug it into the function. Now, plugging it into this function here. There's the function. So x squared plus yz, but don't forget x, y, and z are now functions of t. Right? So everywhere you see in this formula an x, you've got to plug in the formula for x that's a function of t. Likewise y, likewise z. So when we see x squared plus yz, x squared plus y z is computed like that. All right, so this is the function. That's the output, you might say, the output parametric curve. Of course, now this is a real valued function, so it's a parametric curve on the line. It's not much of a curve, but nevertheless, this is output value as a function of time. Okay, and we want to know the velocity, so we take the derivative. Derivative is what gives us the velocity or the rate of change of these output values, and that's just a little bit of calculus. I guess I suppose we should take this algebra to maybe simplify it a little bit first, make it easier. All right, take that, take the derivative, gives you this. And the one little micro detail to remember at the very end is we are interested in the value of the derivative at the moment when t is equal to 0. Now, we're interested in the moment when t is equal to 0, just remember, because we only constructed this blue parametric curve to describe the fact of there being motion at this point. I don't actually care about these points over here, right? We are considering a scenario where we are at that point. And, moving with a certain velocity, thus I need to construct the motion and therefore the curve. But I'm at that point A, and we're at that point A when this function, right, I want that to equal to that, and therefore t is equal to 0. Okay, so at the very end, you got to remember this derivative is being evaluated at the moment when t is equal to 0, so plug in t equals 0, and there you go, 10. Okay, now, go ahead.
Can you go back up real quick? To the picture.
Oh, yeah. Okay, so reminder, y'all, I hope remember this from single variable calculus class. If you're interested in computing a derivative at a certain point, you have to take the derivative first and then plug in t equals 0 last. Right? If you plug in t equals 0 and then take the derivative, it's not the same thing. Right? You're taking the derivative of a constant, you're going to get 0 every time, and that's clearly not right. So be careful with that detail. Yeah?
What did you do from the line 1 plus 2t squared plus that 1?
From here to here? That's just algebra.
Oh.
Yeah, just crank it out. Yeah.
Oh,
Yep, just algebra. Okay, so that's the process. That's how, directly from the definition here, this is how you compute directional derivatives. Very brute force. Okay. Let me show you another one. And I might go through this a little more quickly. It's morally the same kind of a thing. Now, the twist is here we're going to have a function that has two output values. So this is what we call a vector-valued function, because the output values are vectors. Vector-valued function, how do we take a directional derivative? Again, let's assume that we start at a certain point, moving with a certain velocity. And, we start off the process the same way. You take, the point where you're starting, A, plug it in there. Right, those are those numbers, 1, 2, and 0. Here's the velocity at which you're moving. That velocity goes there, thus giving you the 2, the 1, and the 3. So there's your input parametric curve. You plug that into the function. That's the value of the function, xy, comma, yz. Just plug it in. Note that the output is a vector. Well, yeah, it should be a vector because our function has vector values, right? There's two output values. This function has a target that is R2, just like this picture here, right? So when we plug into the function, yeah, we get a vector valued parametric curve in R2. Okay. Right, and then we take the derivative. Gives us this. At the very last second, once the derivative is done, plug in t equals 0, and you get that as your directional derivative. Now, in the last question, we had a scalar valued function. For example, you could think of it as, temperature as a function of position, and so we got a scalar valued derivative. Here we have a vector valued function. We have a vector valued directional derivative. So said differently, as you're moving through this domain with, at that point and with that velocity, these values moving through the target, their velocity, no surprise, it's a vector. Of course, it's a vector. Okay. Last, there's several more examples. I'm going to let y'all read these other examples. That's not terribly different. I do want to make one last observation, and that is the fact that directional derivatives are computed component-wise. Not terribly hard to see why this is true. If you have a function that has several outputs, and if we're taking a directional derivative, let's remind ourselves momentarily, where did directional derivatives come from? Directional derivatives. Well, let's go way back to the beginning here. Directional derivatives. It's a velocity, but specifically it's a velocity of a certain appropriately constructed parametric curve. Directional derivatives are derivatives of parametric curves. We already know from last time that derivatives of parametric curves are computed component-wise. Right? So since this is a derivative of a parametric curve, it's computed component-wise. In other words, if you're taking a directional derivative of a vector-valued function, you can instead take these components, compute their individual compute their individual directional derivatives one at a time, and assemble them into a vector. All right, so I'm going to leave an example of this as an exercise for you guys. The example I would encourage you to do is this one that we just did. Take this function here, this vector-valued function, and compute the components of the directional derivative one component at a time. So we'll start off by looking at just xy. Take xy. That's a scalar-valued function, right? Single output value, just xy. It's a function of x, y, and z. Compute its directional derivative. And here's what's going to happen. You're going to get the exact same input parametric curve. The output values, I hope it comes as no surprise, will be exactly that, namely this, the derivative of which will be 4t plus 5. It's the same algebra. And plug in t equals 0, you will again get 5. Right? And then, likewise, for the second component, if you look at the scalar valued component function, yz, by itself, scalar valued, well, you're going to have the exact same parametric curve in the domain. You're still at the same point in the domain, moving at the same velocity in the domain. Yz will have that value, which will have, again, that derivative, which when you plug in t equals 0 will again give you 6. It's the exact same algebra. Just sort of, you can do them in parallel, or you can do them one at a time. Same algebra. Doesn't make any difference. Okay. All right. Again, the easier way to see this is to realize, well, of course it should be. This is a parametric curve. We already know derivatives of parametric curves are computed component-wise. Okay. Okay, so moving on to the next section, I'm going to start with a calculation. Neat fact about directional derivatives. Right here. And that is if you're computing a directional derivative, and specifically if the vector representing your velocity has a scalar factor, let's say, right? That vector has a scalar factor. Then you can take that scalar factor and factor it out. Or said differently, if you are moving k times as fast through the domain I hope it comes as no surprise that you will correspondingly be moving k times as fast. Your image will be moving k times as fast through the target. Right? It's pretty plausible when you say it like that. Nevertheless, this is an algebraic statement we need to write down a proof. Let me show you how the argument goes to prove that. So we're going to compute this expression here. We're going to come up with that as the result. But let's start with the expression on the left. It's a directional derivative. There's a definition of a directional derivative. Notice all I've done is just write down exactly the definition of directional derivative. My velocity vector is kv. So that goes where velocity vector goes, right? Just plug it in. Nothing really happened there. Well, let's see here. How do I take this derivative? This is not exactly what we've seen before. I'm going to do a substitution. Let me write s equals t times k. All right. A little bit of algebraic gymnastics here. I'm going to let s equal t times k. And in doing so, now notice I have a chain rule problem. This is a function of s, but I'm taking a derivative with respect to t. So the object of my derivative is a function of s. S is a function of t. It's a chain rule problem. So think back to single variable calculus. The derivative with respect to t comes by first taking the derivative with respect to s and then multiplying by the derivative of s with respect to t. Plain old single variable calculus chain rule. Yeah? Everybody good? Okay. We're kind of done. Everything has fallen into place because this is exactly the directional derivative. Now you might say, well, wait a second, whoa, hey, this has got s's in it instead of t's. It's a dummy variable, right? And the directional derivative, there's nothing magic about the letter t. This is the exact same construction. This says form a parametric line. Okay, the parameter is called s. And take the derivative with respect to the parameter. When the parameter is equal to 0. The only difference is the character. This is exactly the directional derivative. Is everybody happy with that? Is that cool? Okay. So that's the directional derivative, and of course it's an easy calculation. ds dt is k. So, as required, that's equal to that. Okay, so a couple different ways to think about this. One way to think about it, and a very handy, in fact, way to think about it, is that scalar factors in the velocity can factor out. That's the way I presented it here. Now, let me say it a little bit differently. Let's come down to this scenario here. Suppose that our velocity vector, I view it as having a scalar factor, and by the way, which all vectors do if you think about it. All vectors are a magnitude times a unit vector representing the direction. You can always do this, right? You take any vector, just factor out it, what is its magnitude, pull that magnitude out, the remaining leftover vector is a unit vector. Okay, so we're going to view the vector v as the scalar v times the vector u, the unit vector u. And when you do that, you take this vector here, factor out the scalar, like I've done there, then you get this statement. And what we can do with that is an interpretation thing. Notice that on the on the left side of the equation, we have df dt. That was the point of the directional derivative in the first place. Directional derivative says what's the output velocity, right? How fast is the value of the function changing? Notice that our right-hand side, the v, let me be sloppy here for a second. It's the kind of the rate of change of the input. Well, it's the speed of the input, but it's, how fast is the input moving? Kinda. Okay, it's a magnitude, not a vector. But what's nice about this is we recover one of the old traits that we observed and made a big deal about back in section 1 of this chapter, which was now we have something that we can view as a factor. This thing the directional derivative, not with velocity v, but the directional derivative where we use the unit vector as our velocity. I call this a unit directional derivative. This has the feature of being a factor. It's what you multiply by input speed to get output derivative. I got to be careful with my terminology. I want to say input change, output change, and it's not. I mean, it's not 100% exactly quite that, because we do have this magnitude here, right? It's the magnitude of the input velocity. It's not the actual input velocity. Nevertheless, the fact that this has the earmarks of being a factor is very satisfying. This is highly reminiscent of our big interpretation of single variable derivative. Is everybody on board? Okay. All right. So this is, like I said, it's called a unit directional derivative. Nice interpretations. The unit directional derivative is a factor. It's the factor that you multiply by input speed to get output velocity. That's what we just showed. Analogously, it is the factor that you multiply by an input jump. Well, the magnitude. Okay, the magnitude of the input jump to get the output jump. Linear approximation of the output jump. So this is an approximation. It's not exact. Right. So a lot like the single variable derivative. All right. Here's a picture of what's going on. Remember, our scenario is that we're considering a case where we're at this point in moving with a certain velocity. We want to know what is the corresponding output velocity, and we're going to come to that by sort of a way of a two-step process. We're going to say, look, we're moving with a certain input velocity. Okay, fine, but let's forget about the velocity. We're moving in a certain direction. Let's just try to understand what this function does as we move in that direction. First, let's understand, look, as you go that way, what's the deal with this function? Let's understand the function in that direction first. We'll deal with our actual speed later, right? As you're moving in that direction, that vector represents the corresponding kind of rate of change as you move with unit speed in this input direction. This is the corresponding velocity in the output direction. So now we feel like we have a fundamental understanding of what this function is doing in this direction. Generally, as you move in that direction, how's the function behaving? And with that fundamental understanding, we then say, okay, well, great. So I'm glad I understand that. Now, I'm not moving with unit speed. I'm moving quite a bit faster. I'm moving faster by a factor. I'm putting an actual factor into the input velocity. That gives me the exact same corresponding factor to the output velocity. In other words, it's just an application of this very first thing that we proved here, that scalar factors factor out. Okay, so that's kind of the idea. And you might say to yourself, what's the point? Right? Why take our perfectly tolerable vector here, right? Divide by magnitude to get the unit vector, and then subsequently multiply by magnitude to recover the directional derivative. Right? It seems a little bit pointless. One could argue, and I largely subscribe to that camp. But nevertheless, there are good things about this construction, and so I want to talk about. Let's go ahead and talk about this construction anyway. Again, it's also a very common construction to see in. When different people talk about multivariable calculus, lots of people fundamentally understand derivatives of multivariable functions as naturally being things about unit vectors. So you're going to see it out there. Okay. So here's one actually pretty nice, I must confess, feature of this construction, and that is, let's consider here, let's look at this picture. I guess I better zoom out to fit the whole picture in. Let's look at a graph of a function from R2 to R1. Now, as you all know, I'm not as big a fan of graphs as a lot of people are. I think they have their value. It is a very narrow situation. It is pretty much just this one, that you can use graphs in this way in a multivariable context. You got to have exactly 2 input variables. You got to have exactly 1 output variables. Otherwise, you just really can't draw this picture, right? Okay, so anyway, that said, it happens sometimes. It's a useful point of view. And in this construction, this unit directional derivative is the slope of the tangent line to the cross section of the graph. It is that point of view, that everyone's first point of view on derivatives, the one that I was kind of poo-pooing, a couple days ago, right? But the one that everyone hangs their hat on in a Calc 1 class, slope of the tangent line to the graph, unit directional derivative is that thing. Now, let me try to persuade you why that is. The slope of the tangent line here would be, let's see here, the slope of the tangent line would be how much output per how much input, right? So the rise over the run, rise over the run, so delta F divided by, the run. What is the run? Well, it's, how far have you moved in that direction? What's the magnitude of your displacement? Look at this equation. There's the rise. There's the run. Right? We've agreed that the unit directional derivative is the thing that you multiply by the distance you've moved in the domain to get the estimate, linear estimate, of the change in the output in the target. So in the case that we have a real valued function, that's a scalar, divided over there, you get rise over the run, directional derivative, unit directional derivative. Okay, so granted, I confess, that's pretty cool. All right. Okay, another point of view on this, by the way. So we wrote here slope of the tangent line. Slope of the tangent line you can also sometimes write as df ds. So remember, we use this s to represent distance, distance traveled. So as you're moving in that direction, right, we can keep track of how far have you, at any given point, how far have you moved in that direction. And df ds, the rate of change of the function with respect to distance, is a kind of a natural thing. So, for example, let's talk about temperature again. I like temperature because it's something that's visceral, but it doesn't require a visual dimension to think about it. Right? So in our dimensionally constrained situation, it's very convenient. So let's think about temperature. And so again, here we are in Durham, and there's surroundings, and you start heading west, head off towards Hillsborough and Mebane and stuff. It's cooler over there, right? And you head toward Raleigh, etc., and it's going to be warmer down there. Okay, how much? Right? If we wanted to talk about how much temperature, how much variation is there in temperature in this general vicinity? Well, one way to answer that question would be to say, look, I'm going to get in the car and I'm going to drive at 65 miles an hour, and I can, with per unit time, I can ask how fast is the temperature changing. And the problem with that point of view is it's peculiar to my experience, right? It depends on how fast I'm driving. If I'm driving at 1,000 miles an hour, the temperature's changing really fast. Right? If I'm driving at 1 mile an hour, the temperature is changing very slowly. So it's that question. If you think about the rate of change of the function with respect to time, you're not talking about the surrounding itself. You're not talking about temperature as a function of position. You're talking about your own personal experience, right? Which is fine, I suppose. But if you want to understand what is going on with the function itself, a very reasonable case to make is, I don't want to know about your own little personal experience. That's fine and all, but per unit distance, as you move in that direction, for every mile that you travel, how much does the temperature change? That's something that's absolute. It's about the surrounding itself. It's about the temperature function, as opposed to your experience of the temperature function. Does everybody see the distinction there? Right. So this is a nice point of view, understanding a function by its rate of change per unit distance, and the unit directional derivative does that. All right, so let's do some examples. These examples that I have are they show different nice features, different conveniences of the unit directional derivative. So I'll categorize those after we do the examples. So, but let's take these examples one at a time. We find ourselves in a forest, and around here. Anyway, there are, sadly, lots of mosquitoes. And let's suppose that we know a formula for, the concentration of mosquitoes, how much, per unit volume of air, how many mosquitoes are there flying around, right? And maybe the function looks like this. This would actually be kind of plausible. Let's suppose there was some stagnant pond at x equals 0, y equals 0. Well, there's a lot of mosquitoes around the stagnant pond, and they don't just stay exactly, right, they fly around looking for somebody to annoy, right? So there's fewer of them the farther you get away. There might even be one way far away, but generally speaking, they tend to be mostly around the stagnant pond where their home is, but they, maybe float around a little bit. So fairly plausible scenario. That said, let's suppose I'm not exactly standing at the stagnant pond at the origin. I'm at this point 2, 1, and I'm on a hike, and I am moving due west at a speed of 3.5 miles an hour. I'm not moving at unit speed. I don't want to move at unit speed. I can walk 3.5 miles an hour, right? So that's the reality. I'm moving 3.5 miles an hour, not unit speed. Okay, so the scenario that I'm interested in of being at a certain point and moving with a certain velocity, I'm not really interested in a unit directional derivative. I want to know the directional derivative. I want to know how fast is how fast is Bob's experience of, mosquito inconvenience, mosquito annoyance, how fast is that changing in reality of how he's actually moving. All right. So we want to compute the directional derivative. Directional derivative. Now you could do that directly. Let me show you how to use the unit directional derivative to do that instead, and that is to take the velocity. Let's see here. Our velocity is. Let me write this down here. Our velocity was negative 3.5, 0. That's due west at 3.5 miles an hour, which we're rewriting here as 3.5 times negative 1, 0. This then is my unit vector, and here's my speed, right? And I'm computing the directional derivative. Having factored out the scalar, I'm computing the directional derivative with the unit directional derivative. Yeah, everybody cool? Okay. Why would I want to do that? We'll talk about the motivation here in just a moment. Anyway, having written this down, the speed of 3.5, well, that's just, look, this is just going to sort of carry throughout the entire calculation. That just sits there. The unit directional derivative calculation, I've got to take our starting point. I'm running out of colors. Maybe I'll use purple. Our starting point, 2, 1, right? Plug that in. I've got to take our unit velocity, that was in yellow, right? Put those together to make our parametric curve, and let's see, yeah, sure. So our parametric curve, the parameterization of our walk, of our hike, is given in red there. Plug that into the function. You get this. I'm skipping some algebra. Letting you guys do the algebra for yourself. Check through the algebra. Take the derivative. You get this. Plug in t equals 0, and you get you get some value that when you multiply by 3.5 gives you this. So that's how the calculation goes down. Now you might say to yourself, we did not need to factor out the velocity there. What's the point? This looks like exactly like the calculation would have carried through in morally the exact same way had I just used the actual velocity here. And here's what would have been different though. What would have been different is that my parametric curve in the domain would have been position plus t times my velocity. My velocity was negative 3.5 comma 0. That's what would have gone in to there. That would have plugged into the function. This factor wouldn't be there anymore. And let me tell you why I don't like this. Now there's fractions that are going to carry through the algebra. It's not that we can't deal with the fractions, but all else being equal, if you can find some little clever way to avoid having to do non-trivial algebra with fractions, I think most of us, all else being equal, would rather deal with integers than fractions. Right? And then now, just to make it worse, let's suppose instead of going 3.5 miles an hour, suppose I was going 3.7684129 miles an hour. You want to deal with that annoying decimal throughout all of the... No, my gosh, no, of course not. Right? So being able to factor out the speed is nice in that it allows you to make your algebra a little bit more convenient. And this is very useful. Everybody on board? Pause for questions. Oh, yeah, I forgot. Good excuse, give me a pause. Okay. All right, here's another example. So we have a graph of a certain function. And by the way, keep in mind if you have a graph of a function, graph means that z equals the value of the function. Z is height. That just means height is a function of position as described by a certain function. So the graph of a function really is just a way of describing a certain, like a hill or, some sort of topography of some sort. So when I say that we have an ant walking around on the graph of a function, it's fairly plausible. Ants walk around on hills all the time. Okay, so the ant is at this point. Well, so he's on the graph directly above that point 2, 0. And he starts walking in the direction indicated by a certain vector. So he's walking in the direction 1, 1. So you might say he's walking northeast, right? He's not walking with velocity 1, 1. He's walking in a direction indicated by the vector 1, 1. And the question asks it's not asking how fast is his altitude changing. The question is asking what's the slope of the side of the hill, the path that he's walking on. How steep is his path? What's the slope there? So this is a question about the environment of the ant, right? It's not a question about the ant's experience. How fast is he, raising his altitude per unit time. It's not asking that at all. It's asking what's the slope. So I want to make a big deal about the difference between the rate of change per unit distance, which this is about, versus rate of change with respect to time, which this is not about. Everybody on board? Okay. All right. Feel free to ask a question. It's a subtle point, so. Okay. All right. Okay. So we want to compute here. The answer to our question. The slope of a graph is the unit directional derivative. So here, the unit directional derivative is not playing the same role as it did here. Here, the unit directional derivative was a tool for computing the directional derivative that we actually were interested in. Here, the unit directional derivative is the thing that we are actually interested in the first place. All right, now that being said, how do you compute the unit directional derivative? There's a temptation to say, and we've already seen how unit directional derivatives are always just so wonderfully easy to compute, and not so. Unfortunately, we got lucky in this case. In this case, it happened to be that the unit vector was convenient. The unit vector was convenient because it had integer coefficients. Here's the thing. In this case, our unit vector is inconvenient. a unit vector does not have integer coordinates. It's the original vector. That vector is the one that has integer coordinates. So, super annoying. I mean, the thing that we want is harder to compute than this other thing. That's, inconvenient. But keep in mind, there's this factor out scalars, feature of directional derivatives. So I can take this formula for u, that formula for u right there, and I can rewrite then u as being this convenient vector v divided by its magnitude, right? Factor out the scalar, pulls out the square root of 2, and now we find ourselves very conveniently computing a directional derivative where my velocity vector has integer coordinates, which makes the algebra convenient, no fractions. And then just, don't forget about the fact that scalar comes for the ride all the way through the calculation there. But it's a factor sitting on the side, so it doesn't make it hard. Yeah? How we doing? Okay. All right. So, couple of different applications. Sometimes the unit directional derivative is easier to compute and therefore a tool for computing directional derivatives. Sometimes the unit directional derivative has a natural geometric interpretation that makes it exactly what you want to understand in the first place. So in other words, sometimes unit directional derivative has a conceptual advantage, but not so much computationally. All right. So my last example that I want to show you is really kind of an anti-unit directional derivative example. There is a tendency for people to think that tools that are presented later in a course must be preferable, more powerful, more sophisticated replacements of the weak tools that we saw earlier in the course. And I just want to point out that's not what's happening here. I'm not in any way, by the ordering of these sections, I'm not suggesting that unit directional derivatives are the superior, directional derivatives 2.0. No, not at all. It's a different construction, right? With different interpretations and different situations where it's convenient, right? But it's not intended to be a replacement. So let's look at this example here. Suppose I wanted to compute a directional derivative, and there's my velocity vector. Well, the velocity vector's got integer coefficients. Be a pretty straightforward calculation. Right? Now, suppose that instead of computing this directly, suppose we decided we wanted to compute the directional derivative, with unit directional derivatives, we would instead, alternatively, have to take this vector, divide by its magnitude, and then compute the unit directional derivative, which would be in the direction of the vector, the unit vector pointing in that direction, 2,7 over the square root of 53, sorry. And our point A. So these are our two alternatives. I can just compute this straight up, or I could go to the trouble of turning that into a unit vector, having a more inconvenient calculation to go through here because I have a stinky unit vector there that's got fractions and radicals in it, and then at the end of having done, of course I don't know why I divided, that's supposed to be a multiply, and then having done that, multiply back by that square root in the first place. Absolutely pointless. Everybody see how completely pointless and silly this would be as a process? So one of the homework exercises, I'm going to make you do this, just so you can feel it, right? I think once you've actually done something pointlessly inconvenient, it's a wonderful sort of teaching tool of, okay, now I don't ever want to. Oh my, that's a waste of time, right? It's a good way for keeping your heads up in the the future. So anyway, so heads up here, note one of the homework exercises is like this. Okay. All right. So moving along. So let me go back now to something I was talking about before. So I was talking about this the different uses of the term. So the term directional derivative, right? So it means different things to different people. And I just want to kind of put a final thought on that. So I use the term directional derivative, as I have in the book here, for the more general construction. You give me an input velocity. Hey, whatever your input velocity is. And we compute the corresponding output velocity. This general construction directional derivative. This is a common interpretation of the word directional derivative. I've asked some mathematicians. This is actually kind of funny. I asked one mathematician, which interpretation do they take? He wasn't even aware that some people did it the other way, right? And vice versa, right? It's a very pervasive problem of ambiguity of the term. So that term is that use of the term directional derivative is very common and standard in some books, and for some people. The term directional derivative applies to the idea that in this book I am calling unit directional derivative. Right? So when you hear, in your future math dealings in math classes, or once you have a career in grad school or whatever, if you see the term directional derivative, you have to heads up right there and say, wait a second, okay, who is this writer? Who is this speaker? And what do they think the term directional derivative means? And if you see that this person, if you see some indication, like maybe they say, okay, so we take the unit vector, then you just think, okay, so this person is using the term directional derivative in the way that I would think of naturally as being unit directional derivative. And then you have to interpret accordingly to how they're using the term. So anyway, like I say, heads up. Okay. All right, so moving along, we're going to talk about something called partial derivatives. This is a further special case of directional derivatives. So directional derivative is a general construction. Velocity vector can be anything. Unit directional derivatives require that the input velocity be a unit vector. And with that stipulation, we get an extra interpretation, right? Unit directional derivatives are slopes of graphs. Unit directional derivatives are rate of change with respect to distance. The extra requirement on the input velocity gives us extra interpretations. By the way, it's a general fact in math. The more narrow your application of an idea, the more tools you have to work with and the more results you can prove. So the less you talk about, the more you can say about it. Right? Okay. All right. So a partial derivative is, we're just going to narrow our consideration even more. We're not going to allow the velocity vector to be just anything. We're going to continue to require that the vector be a unit vector, but even more than that, we're going to further require that the velocity vector be a standard basis vector. So it's got to have length 1, but it also has to point exactly parallel to one of the coordinate axes. So this is a really narrow consideration here. All right, does everybody see the requirement here? And it turns out that something nice happens here, something really nice. So here's how the calculation goes. Let me remind you, here's our definition of directional derivative. Now, this is what we're calling a partial derivative, namely that velocity vector is a standard basis vector. Right, so that is a standard basis vector. Let me remind you that a derivative, right, is defined just like it always has been. So let's write down the derivative as a limit. Notice that this being a standard basis vector means that there's going to be a lot of zeros in this calculation. Right? Lots of zeros. There is a single 1 in the ith position, right? This being the EI standard basis vector means there's a 1 in the ith position there, and other than that, all zeros. Okay. And we can simplify that a little bit. I mean, again, as many zeros as there are, most of these coordinates don't change at all. It's just the one coordinate there that changes at all. Most of the rest of the coordinates stay fixed. So this expression here is actually what we end up getting out of the deal. And notice that coordinate starts at A1, ends at A1. That coordinate doesn't change. For the purposes of computing this directional derivative, the first coordinate does not change. The first coordinate is constant for the entire purpose of this calculation of this very special directional derivative. Likewise, the second and blah, 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 most of these coordinates don't change. All these coordinates here don't change. The last coordinate doesn't change. Most of the coordinates don't change. Only one coordinate changes. Right? That ith coordinate starts at AI. And it ends at, AI plus h. Okay, so now what I want to do is I want to look at this expression here. Keep in mind we're computing a directional derivative. Let's look at this formula here and ask, does that look familiar? And this actually looks extremely familiar. That looks just like a single variable derivative. Right? We've got some expression. I'm going to think of all of the other variables as being constants because, well, they are. They're not changing. A1 doesn't change. Let's call it a constant because it is a constant for the purposes of what we're doing here. And the only actual variable, the only thing that's changing, I'm going to plug in to the function. Then I'm going to add h, plug into the function, subtract, divide by h. Notice we're dividing by exactly how much we're changing the input. This is a single variable derivative. Calc 1. Everybody on board? So it's the derivative, it's the plain old single variable derivative, Math 111L, of the single variable function that you get when you just choose to view all the other variables as being a constant. This is awesome. So that means it's super easy to compute these things. So here's a multivariable function. Let's look at this guy right here. Multivariable function. I want to take this very special kind of directional derivative. We're going to take this, directional derivative in the E1 direction. The argument above says I can just choose to view all of the inputs as being constants, and then just take a calc 1 derivative of the remaining function. So let me zoom in for focus. So I'm going to view x as being a function. I'm going to view y as being a constant because it is a constant. All this becomes constant. See, look at this. I'm moving in the E1 direction. Y doesn't change as you move in the x direction. Right? So all that is a constant. Right? I'm taking a derivative here, taking a derivative with respect to x of x squared times a constant plus a constant. And that's easy. Right? The derivative of x squared is 2x. The constant factor of y cubed is a constant, so it stays there, comes along for the ride. The derivative of the constant y squared is 0 because it's a constant. We're treating y as a constant because it is a constant. So that was easy, right? Now let me just remind you of what we've computed here. We've computed a directional derivative. Have we computed directional derivatives in the past? Well, you got to take this, you got to make a parametric curve and work out the coordinates of the parametric curve and plug into the function and get this bigger expression, and then you take a derivative of that great big thing. It's a whole thing, right? Here we just took a directional derivative by saying, you know what, I would like to view that as a constant, and I'd like to view that as a constant, and I have easy rules for how to take that derivative, and therefore I'm done. Much easier. Okay, so this is what you get for making this assumption. Again, you know, keep in mind, like I was saying before, the more you narrow your attention, the more you can say about that very special case. Right? So here we are narrowing our attention. We're not just pretending we have a unit vector in the velocity. We're very narrowly saying, yeah, and furthermore, these are standard basis vectors. What we get out of it, the extra conclusion that we get, is ease of computation. Okay, so this is called a partial derivative. Partial, the idea of the term partial is that we're taking the derivative, you know, here we have these two variables, x and y, and we're taking the derivative just with respect to x. We're not considering all the variables. We're saying, okay, only x is changing. Just a part of the input variable, of the complete list of input variables, just part of it, just that one is allowed to change. So partial derivative, yeah.
Do you get any larger conceptual information by taking the partial derivatives with respect to each
Yep.
vector?
Yeah, that's going to come. We're going to talk about that later on. Some really cool stuff happens, and it's hard to see it coming. There's some big observations that we have to make first. But yeah, if you know the partial derivatives with respect to all of the input variables, it turns out you can do awesome things with that. So yeah, but we have to wait. It's going to take us a couple. It'll be well after the exam. Yeah. Okay. Anybody else? Okay. So here's the definition. Let's talk about the notation first. Here's the notation that we use. Notice that does not look like the notation that we've used up to now for directional derivative. Most of the time, day in and day out, nobody writes this for partial derivative, even though, I mean, ultimately, I cannot emphasize enough, partial derivatives are directional derivatives, right? Definitely. They're directional derivatives, very special kinds of directional derivatives. But it's very convenient to write it like this as, well, look, we're just taking a derivative. It's just with respect to one of these variables. Now, another thing about the notation, you'll notice that those D's look kind of funny. Right? And, in fact, they are not D's. That is not a D. This is a D. Right? So that little symbol, though, it's not a D. And by the way, it is incorrect to write D. If you write a D instead of that little weird little symbol there, it's wrong. Right? So that making a different symbol is our recognition of the fact that, well, we have to confess, this is a function of several variables. That's not a single variable function. You can't talk about an actual single variable derivative of a function that is not actually a single variable function. It just doesn't make any sense, right? So putting this little symbol there is our way of recognizing, doff of the cap, that, okay, granted, yes, I know it's not really a single variable function, but what I want to do with it has the net effect. If I get to treat it like a single variable function, and along those lines, you know, I want to pretend like I'm taking a single variable derivative. So if there are multiple input variables, you're talking about a partial derivative, and you got to make that symbol. So it's another one of those things where you kind of have to practice. Like, you know, you all spend a bunch of time, or at least I suggested you spend a bunch of time making rows. Right? You're going to learn how to make a row. It's not a P. You can't make a P. It's not a P. Likewise here. You know, spend 60 seconds just figuring out how to make that symbol, and resist. You're going to have this overwhelming urge to do that. Right? And you got to resist that urge, because that's wrong. Okay. Everybody on board? So the partial derivative, from an interpretation standpoint, it's a special directional derivative. Special directional derivative defined by, of course, the usual formula. But it is also effectively a kind of a single variable derivative, and day in and day out, that's how people compute these things, like we just discussed. Okay, another notation. This is, you might say, a kind of a Leibniz-like notation, right? It kind of looks like, sort of dy dx. Structurally, that's what the notation looks like. Y'all remember, of course, for derivatives, there's this alternative notation where you put a prime, right? That's Newtonian notation. You say f prime. There is a kind of Newton-like notation for partial derivatives, and that is, well, you can't just say prime. If you said f prime, you're not indicating what variable are you taking the derivative with respect to. There's several variables. Prime is ambiguous. Okay, so, but just making, the variable that you're taking the derivative with respect to, making that a subscript. Standard, understood notation, sort of a shorthand notation for taking the partial derivative with respect to that variable. Okay. Likewise, sometimes if you're looking at maybe a graph, or if you, for whatever reason, if you have a name given to the output value, so the function is called f, but if you've given the name z to the output values, sometimes people will write, again, x as a subscript, indicating derivative with respect to that input variable. Okay. All right. Okay, let's see here. Here we go. Okay, so good news. Not only are partial derivatives easy to compute, but partial derivatives are computed component-wise. Why are partial derivatives computed component-wise? Well, partial derivatives are directional derivatives. Directional derivatives are derivatives of parametric curves, and we saw directly that derivatives of parametric curves are computed component-wise. So all these kinds of derivatives that we're talking about, they're all just different special cases of derivatives of parametric curves that we've constructed in this certain very special way. So they're all computed component-wise, and that's super handy. Okay. The interpretations, there's nothing new here. Partial derivatives, just like unit directional derivatives, which they are factors that you multiply by input changes to get output changes. It's not news, right? They are unit directional derivatives, therefore they behave like unit directional derivatives. Okay. Likewise, they are directional derivatives, therefore they behave like directional derivatives. They are, this is, I guess you could argue I kind of have these out of order. They are unit directional derivatives, and therefore, just like unit directional derivatives, which they are, they compute slopes of tangent lines. Okay. Slopes of tangent lines, though, specifically in the direction indicated by whatever that input standard basis vector is. So you're taking a partial with respect to x. That means you're going to take a cross-section of your graph in the x direction. Right. You take a partial with respect to y, you're taking a cross-section of your graph in the y direction. Okay. All right, so here's some examples. Quick examples. Here's a function of x and y. There's a lot of lingo in the statement of this question. The lingo is all sort of necessary. I mean, it gets abbreviated. I'll talk about that in a moment, but let's walk through the lingo here. Here's this function. I'm going to look at the graph of this function. Then I want to take a cross-section of that graph. Then I want to take a tangent line to that cross-section of that graph. And we want to know what is the slope of the tangent line to the cross-section of the graph of this function. A lot of lingo. Okay, but just keep in mind, all that lingo, that's just, all that's saying is, I want to compute the thing that I just got through arguing partial derivatives compute. Right? So, now, how do people talk? Most of the time, people say, what's the slope of the function? Okay, well, again, it makes the hair on the back of my head stand up. You can't talk about a slope of a function, right? Slope refers to something geometric. So we're talking about the graph of the function. Well, the graph of the function this is a two-dimensional surface. It's got slopes in lots of different directions. Okay, so I mean the slope of the cross-section in a certain direction. The x direction, in this case. how do we really, to get right down to it, talk about slopes of curves? The cross-section is a curve, of course. The way we talk about slopes of curves is by talking about the tangent line to the curve, and there's a well-defined notion of a slope of a tangent line. So, I mean, there's a bunch of lingo that has to get said just to make it precise exactly what we're talking about. But casually, people, and I don't encourage this, but be prepared. In reality, you're going to hear people say, "What's the slope of the function?" In the x direction, and then you roll your eyes a little bit, and you interpret that this is what they meant, and then you calculate in the way that they intended. Slopes of tangent lines, the blah blah blah, are partial derivatives. Partial derivatives are easy to compute, right? If we want to take the x partial of that function, x is the only variable that we treat as a variable. All the other variables, y in this case, are constants. We treat them like constants because they're constants, because we're moving only in the x direction. Y is not changing. So we treat y as a constant. All of that is constant. The derivative is super easy. Plug in the point in question, and there's your answer. Everybody on board? Any questions? Feel free. Yep.
When you say cross section, do you mean like you're cutting the function at a certain?
Yeah, totally. So let me go back to where I have a picture. Let me go back to so this picture here, right? So when we're talking about here's our graph of the function, right? So height is a function of position. And if I say what's the slope of the graph, it doesn't really make any sense. But if we're talking about, in a certain direction, that says we're taking a cross-section, vertical cross-section in that direction. That cross-section is going to be a curve. Yeah. And so we can talk about the slope of, the tangent line to that curve. But casually speaking, we talk about the slope of that curve. Does that make sense? Yeah. Okay.
So that's in the x direction.
Well, now, the picture I drew here was, arbitrarily, whatever direction you might be looking, whatever that unit vector might be. But yeah, when we're talking about a partial derivative, don't just pick some arbitrary unit vector. Partial derivative in the x direction, or partial derivative with respect to x, means we look at a cross section in the x direction. Yeah, totally. And there were some hands back there. You good? Are you okay? In the back?
Yeah, my eyes, yeah.
Okay, yeah, cool. Okay. Yeah, we have 60 seconds left here. Okay. Let me just get to a good wrap it up point. So let me do one other quick example. This would be a good place to stop. Suppose a bird's flying through the air, and we've got a certain point and a certain velocity, right? So you hear directional derivative, right? If you're at a point, certain velocity, and you want to know how a function's changing, right? How fast is the function changing? Here's the function. What we want to compute here is a directional derivative. Now again, you can just brute force this process. It's totally fine. But something really nice happens. We can take advantage of the fact that, our velocity has a lovely unit vector factor. Right? If I factor out the speed of 5, then I can rewrite this as 5, and then I have a unit directional derivative. But furthermore, not only is that a unit directional derivative, it is also so this here. Oh man, I got the. That's not just a unit directional derivative. That's a unit directional derivative in the direction of a coordinate axis. That's a vector in the y direction, right? And so it's partial derivative. And partial derivatives are super easy to compute. And you notice I didn't have to parameterize anything. I did have to use the chain rule. That's going to happen, right? But I didn't have to parameterize anything. I just treat everything else as a constant, take the derivative, don't forget the chain rule, and we're done. Oh, very convenient. Okay, great stopping point. Y'all have a great weekend. Don't forget we have an exam on Monday. and I'll send you an email. By the way, none of what we talked about today is fair game for the exam. So I sent an email to you all yesterday noting this. None of what we did today is fair game for the exam. It will be for the second exam, obviously. But so I assume you will not start these homework exercises until after the exam. Right now, I'm sure we all agree you should focus all of your attention on studying for the exam. So plan to start on these exercises on Monday afternoon. Okay, see you later. Oh, and I have homeworks to return. Let's see here. Let me stop the recording.